think we'll slowly start, right? Okay. Okay, so good morning, everybody. I'd like to welcome you to Chemistry 580 and Physics 580, a special topics course on algebraic and diagrammatic methods for many-electron and other Many-Fermion systems. My name is Piotr Piecuch. You can call me Piotr. If you manage, you can call me Peter. It's the same thing. And with the last name, well, okay, whatever you make out of it is fine. Okay, don't worry about that. As you may know, I am visiting the chemistry department at Washington University. My permanent base is the chemistry department and also the Department of Physics and Astronomy at Michigan State University. And I'll be your instructor. I already communicated with you by email, explaining some basic pieces of information about this course. As you know, we have a website, so I'm showing it here, where you can find all the important information about the lectures, the homeworks, the exams that we'll have, the books and the reading materials, handouts, also the grading system that are applied. So you can see it now a priori. When it comes to handouts, they will be available they are already actually available in the Blackboard system, where you can just log in and see them, but I'm going to be also bringing them here. So I guess there's one set for you as well. Okay. So in those handouts that I'm giving you today, you're going to find the course content. You're going to find essentially the sort of PDF version of the main web page for our course. And I also gave you two other pieces. One of them is essentially, I would say, 1/3 of the lecture notes written by Professor Josef Paldus, one of the pioneers of many-body methods in electronic structure theory in quantum chemistry, a very famous scientist. This book does not have a formal textbook. This course does not have a formal textbook, and I'll be using various books and various pieces of information, and I would say also my own experience. I work in this area, so I'll give you my viewpoint of what I think is useful. But those lecture notes, are related, so it's good to really have them around. But of course, my main advice is just take good lecture notes. Just copy what I'm writing on the blackboard. There will be a lot of derivations, a lot of equations written up. I will try to derive everything I'm going to say. I don't want to leave you with an impression that certain things cannot be derived in the classroom. No, everything can be done in this way, so we'll do it. Of course, you may have questions. If there's a short question, I would say, since we're recording this, if there is a short question that, I wrote something incorrectly, maybe you will catch me in this way, or you simply something isn't clear, please, of course, do not hesitate to ask. For, I think, longer discussions about the topics of this course, let's postpone them maybe to after classes. I'm happy, I'm available to all of you anytime you need me. And I put the formal office hour, but that doesn't mean that I'm going to be just using that hour to talk to you. We can arrange for this very easily. One important thing about this class is that this class is recorded, videotaped, and the idea is that, of course, this is useful for you. You can simply watch it as many times as you please. But it's also important for us because there is the parallel course at Michigan State University called Chemistry 993, which is also a special topics course taken by students who are enrolled there. And what's going to happen is, if all works as we hope to have it, these classes will be recorded and then made available through Blackboard to the students at MSU today in the evening for the class today, and then on the evening on the same day as class is here. So essentially we'll have students, another group of students, your peers at MSU, who will be learning the same material, and they will have homeworks, they have all these things that you're going to be doing here the same way. So I hope that this works in the end. Never done it this way, so we'll see. Before I go on, I would like really to spend just a couple of minutes to thank several people who have helped us to organize this class. As you know, I'm not from here. So I have to quickly learn how things work around here when it comes to, for example, teaching classes. So my special thanks go to Rachel Dunn, Chris Thuet, Angela Potter from the chemistry department, and also Robert McFarland and Lamira Martin from the library. You know, they really were very instrumental in setting up various elements of this class. We have partners at MSU, so I would also like to recognize them here. Steve Poulios, Chris Pfeffer, Paul Reed, and Tom Carter from MSU, and also Cindy Stone from MSU's library helped us a great deal to organize those parallel classes at MSU. I would also like to thank Katie Diekemper for helping us with the Blackboard. You know, we have to make sure that students from MSU can actually log into Blackboard system here to learn various things about the course. And my very special thanks go to members of the Teaching Center at Washington University in St. Louis who will be doing the recording and then placing these videos online. That's extremely important here. So I'd like to thank Mary Stewart, Scott McCain, who is actually here behind the camera, and Mike Floyd. And my very special thanks go to our wonderful camera person who is going to be recording us, Nicole Ibalo. She's going to be with us for the rest of this semester. So this is all great. Thank you so much for doing this for us. One thing that, of course, we discussed by email, but let me emphasize this once again, is today's class is just normal, goes from 9 to 10. As of Friday, we'll start our classes at 8:30 in the morning. So we'll have these extended classes with a short break in the middle. So in this way, I'll be able to really derive more and go into various details, rather than just skipping the material and telling you, well, this is true, but I can't prove it, don't have time. I'd rather actually prove everything I'm going to say. So that's the purpose of these extended lectures on Friday in the morning. Okay, so I guess that would be everything from the introductory point of view. Let me maybe say a little bit about the course contents. So you have it here in a sort of fairly detailed manner. This class is divided into sort of, you can say, roughly speaking, two big parts. The first part is learning basic algebraic and diagrammatic mathematical tools that allow us to handle various types of expressions that show up in various types of many-body theory considerations. So in electronic structure theory or nuclear structure theory, if you use basis sets, okay? Various matrix elements, you want to compute them efficiently so that eventually you can end up with programmable expressions. We eventually write computer programs for these things, and it's good to know all the mathematical tricks that go with it. So we'll talk about second quantization, we'll talk about Weak's theorem, we'll talk about Weak's theorem in a diagrammatic form, we'll talk about whole particle formalism and things of that sort. Once we cover this part, we'll switch gears and we'll start talking about physical theories that apply to areas such as electronic structure theory or nuclear structure theory. The two most important theories covered here will be many-body perturbation theory, which has played a big role in the history of many-body concepts in physical sciences, and then Kappa-Castells theory in the end, sort of as the biggest highlight, I guess, of this course, hopefully. We'll also talk a little bit about mean field theories, such as Hartree-Fock, or the concept of maximum orbitals due to Bruckner. I will not spend a lot of time on Bruckner, on independent particle models, mean field theories. That will be a separate class, really. Then you will have to talk about density functional theory and things of that sort. This is not this class. In this class, we, of course, it's useful always to talk about mean field theories. Here, actually, one reason I want to talk about them is that we need some sort of a mean field calculation before a calculation where we include correlation, simply because we need spin orbitals or single particle states to define our many particle wave functions. So that's what Hartree-Fock theory can do for us, for example. So that's one reason. Another reason is that I'm going to try to prove Hartree-Fock equations, for example, using Fowler's theorem, which is one of those beautiful theorems that you really would like to know if you haven't seen it yet. And the third thing is that you will actually see that when it comes to theories like Hartree-Fock, all you need to do to derive Hartree-Fock equations, when you know enough, is to draw one diagram. One diagram is enough to derive these equations. Those of you who know already how to derive Hartree-Fock equations, you know that in a conventional presentation it takes a few pages to do that. Well, it will take us one diagram. Well, that tells you that if I draw 100 diagrams, not a big number, I probably can go into very advanced theories. that include correlation. So that's going to be the purpose. So in the end, what I hope will accomplish here is that you will end up with sort of hands-on tools that allow you to derive all kinds of expressions, including the ones that you have in your research. But in doing all of this, I have to keep in mind that the audience here, the students who are listening, they have different backgrounds. We have a number of chemists, experimental, and we have and physicists. We have theoreticians and experimentalists. You know, we have people with less experience and more experience. So I have to somehow combine all of this. So what I'll do in the initial few lectures, I'll set essentially the stage. Okay, I'll start simple, assuming that you know quantum mechanics, but you don't necessarily know a lot more about many-body theory. Okay, those of you who have already seen second quantization or Weak's theorem may feel a little bit bored, but please bear with me. At some point, you'll certainly see new things, and maybe even in those initial lectures, you'll see a different presentation of what you already know. Okay, so I hope that we can do this. Okay, so I guess I should start lecturing, right, at the blackboard. Okay, so let me use these fantastic devices here. Room control. I think I can do the mute, and I can go to room control and up. Okay, so we can see some blackboards. And let me start. I'll start briefly with the motivation for this course. Of course, I think that all of you already know what it is, but just briefly for everybody. My research, I'm a theoretical and computational chemist, and I also work in the areas of many-body physics. So much of my activity is dedicated to the development of new quantum chemistry approaches, including correlation effects. So as a chemist, let me say, what would be the motivation for this course when you are a chemist? Okay? Well, from the microscopic perspective, what you need to do, you need to solve, of course, the Schrödinger equation for a molecular system. So let me first write the Schrödinger equation. IH bar, di psi over di t. The Hamiltonian is stripped H psi. Okay? Where H is the molecular Hamiltonian, which I'll write in a moment, and psi is the molecular wave function. Well, in order to spell these concepts out, let's start with the wave function and its various dependencies. So what is a molecule from the microscopic perspective? It's a certain number of electrons moving in the external potential created by the nuclei. Nuclei in chemistry are just point charged particles. That's all they are for nuclear theorists, of course. That's a big exaggeration, right? But that's what they are for us in chemistry. So what, if I have, say, electrons, I'm going to label them with letters like I and J. So we'll have let's assume that we have n electrons, so I goes from 1 to, say, n. Okay? Then we'll have some nuclei. I'm going to label them here with letters like, say, capital A or capital B. So let's assume that we have capital M nuclei. Well, then I can sort of, in this coordinate system, I can introduce various distances that we need to have. We have, let me sort of do this very quickly like this. So the distance between electrons I and J will be Rij. So R12 will be the distance between electrons 1 and 2. Okay? Then here we'll have Ria for the distance between electron I and this nucleus A over here. Here I'll have Rjb. That's the distance between this electron and that nucleus. And then of course I can go across. This will be a distance between electron J and nucleus A. And then this one here will be a distance between electron I and nucleus B. And here for the distance between two nuclei, I will have Rab. Well, lots of things to write just for a few electrons and a few nuclei. Now you have to imagine that of course molecules can be as small as, I don't know, water or hydrogen fluoride. That's just 10 electrons and 2 nuclei. Well, that's a complicated mechanical problem you have to deal with. You have already, 12 particles to deal with. But of course, as you know, molecules can get as big as you please. All right. If you go to DNA, you'll be talking about thousands of electrons and hundreds and so on of nuclei. So this is really a complicated problem which we want to solve. Okay, to understand chemical reactivity, chemical properties, and so on. And I'll have a little slide maybe summarizing all of this. But then, of course, the key is to write a Hamiltonian in order to solve this equation. Of course, we can also solve the time-independent Schrödinger equation, which will be an eigenvalue problem. So I'll write it this way, where, for ground and excited molecular states. So let's write the Hamiltonian. So the Hamiltonian consists of several terms. There will be kinetic energies of all electrons, kinetic energies of all nuclei. We'll have interactions of electrons and nuclei. So we have a potential energy term that describes, or maybe I start with electron-electron interaction, then we'll have the electron-nucleus interaction, and then we'll have interactions among the nuclei. Okay? Those are the terms in the Hamiltonian. Let's spell them out. So the kinetic energy of electrons, it is of course a very well-known formula for all of us, minus h bar squared over 2me, a sum over I from 1 to n. We have Laplacians for each electron. So as a reminder, a Laplacian is the sum of second derivatives over x, y, and z coordinates of electron I in this case. So let's just write it. All of this is of course very elementary, but in this initial class we probably should do this. Okay, so that's the definition of the Laplacian for electron I, and then you have to sum over all electrons. Me here is the mass of an electron. All right. Well, then we have the kinetic energies of nuclei. Okay, so again we'll have a summation minus h bar squared over 2 capital Ma. So M sub A is the mass of nucleus A, and I'm summing over all nuclei A from 1 to capital M. I said we have M nuclei, and then we have a Laplacian here for nucleus A. So again, to be formally correct for good definitions, sum of the second derivatives over x, y, and z coordinates of nucleus, say A. So I'm going to label x, y, z with A, and I'll use capital letters x, y, z for nuclear coordinates to distinguish from the electronic coordinates, which are lowercase x, y, z's. Okay, and then we have the various potential energy terms. So let me maybe open this up. See it better, hopefully.
All this is in Cartesian coordinates.
Yes, right now, yeah, and this is a choice one can make. And then we go with the electron repulsion terms. Of course, here it all depends how you do it. But in a non-relativistic case, it's just the Coulomb law that you have to apply. So we have a summation over of terms which look like E squared over Rij. It's a repulsive interaction. We're summing over all pairs of electrons in a system. Okay, and then we'll have E here is the charge of an electron, obviously. Then we have VEn. Here. So this is an attractive interaction. We have negative electronic charges interacting with the positive charges of nuclei. So we have a summation over I from 1 to n. We have a summation over A from 1 to m. And then we have ZA E squared over R IA. Z is the atomic number. Okay, so this is just the Coulomb law applied to IA pair of particles, and I'm summing over all of them. And then the final term is the nucleus-nucleus interaction. So this is again repulsive. We're summing over all ordered pairs of nuclei. We have ZA, ZB, E squared over capital RAB. Okay, so again, Coulomb law applied to pairs of nuclei. That's what it is at the outset. Well, you want to solve this. So of course, we have to say, what is the wave function? Wave function, of course, given the coordinates that we have here, depends on all electronic coordinates. So I'm going to have n sets of electronic coordinates. I'm going to use letters little x, not for x coordinate, okay, but for simply a bunch of electronic coordinates. For electron, say 1, it's going to be x1. Maybe I'll put the wavy line. If I forget to do this, please forgive me. That's what I'm going to mean here. x1 stands here for xyz coordinates of an electron 1, and the spin. Electrons can be in the spin up or spin down states, the alpha or beta spin states. So formally, if you follow the non-relativistic description, we're going to have sort of 4 coordinates for each electron, x, y, z, and the spin state. So this will be, say, x1, y1, z1, and the corresponding spin, I'm going to write it as sigma 1, which could be alpha or beta, right? The spin up or spin down wave function. And then I can do it for electron 2, and I can do it for electron n, but that's not the end of the story. That's just electrons. Now we have nuclear coordinates. Say, we can choose Cartesian coordinates for now, all right? So we have then R1, up to Rm, where each of these r's is again x, y, z coordinates for nucleus 1, the nucleus 2, and so on. So this is very complicated, right? Obviously, for anything other than, I guess, hydrogen atom, right? So, you know, that's what we are dealing with here. And the thing now is, how do we deal with this here? Actually, in terms of notation, let me maybe do it right away. I don't want to repeat all these symbols all the time the same way. Okay, so for the consistent, to compact this notation a little bit more, I'll use capital X. That means all electronic coordinates that we have. You know, the 4n formula that I said. And then after semicolon, when I say R, I can put these wavy lines, pretending that it's bold. Okay, for all the nuclear coordinates. Okay, that's so that we remember about the dependencies. Okay, what do we do right at this point? Well, at this point, we have to, typically, we do some simplifications. Fortunately for us in chemistry, electrons are much lighter than nuclei. An electron is about 2,000 times lighter than a proton, and most nuclei in a molecule will not be just protons, right? So that means that we can assume, and I'll comment on that assumption, but let's first assume that our molecular wave function can be factorized and written as a product of two states. There will be an electronic part. It depends on the electronic coordinates, but parametrically on the nuclear coordinates. And then there will be a wave function chi, which describes the nuclear motion, the motion of nuclei in the presence of the electrons and other nuclei. Now, I will explain these as we go on. What you do, you take this form of the wave function, insert it into the Schrödinger equation, manipulate, neglect small terms that couple the electronic and nuclear motions. That's the source of the so-called Born-Oppenheimer approximation. Goes back to a long time ago, almost the beginning of quantum mechanics. And you end up with two sets of problems. So you split the original problem into two. One will be the problem for electrons. Okay, so there will be an electronic Hamiltonian, which I'll define in a second. Okay, and then this will be simply an eigenvalue problem for this part, the electronic wave function. Okay, so let me write it this way. Again, I guess I should take wavy lines. Just a bunch of sorts of one variable, but we have many of them. Okay, so this is an electronic wave sort of Schrödinger equation, which you solve in the following way. You freeze the nuclei in some fixed position in space. You solve the electronic Schrödinger equation, written here, with the electronic Hamiltonian, which I'll define in a second. Well, then, you can change the position of nuclei and resolve the Schrödinger equation. And you can change it again and resolve. And if you do it with patience, okay, if I say do it for a diatomic, for diatomic, my good coordinate could be just the distance between the two nuclei. Okay, so hydrogen fluoride, say between the hydrogen and fluorine nuclei. Okay, so I solve it for one distance, then another, then another, then another, then another, then another. And I end up with the parametric dependence of the energies, electronic energies, and electronic wave functions on the nuclear coordinates. This leads to a very important concept in chemistry, which we describe as the potential energy curve that you see here, or the potential energy surface. Okay, and I'll now explain how important it is. Before I do this, of course, this is an eigenvalue problem which has ground and excited states. So you're not computing one wave function. You can actually compute, well, as many of them as you know how to compute, or as you request in your program that is using this for you, doing this for you. So I'm going to label them with an additional letter, say mu. Okay, I will put mu here, and mu here. That mu, if it's, that's a bunch of quantum numbers that you need to characterize a given electronic state. For simplicity, if mu is 0, that's the ground state. If mu is 1, that's the first excited state. If mu is 2, that's the second excited state, and so on and so forth. Electron. So in other words, I will not end up with one curve, but more of them. Okay, maybe there will be another one. Okay, and then another one. I don't have space here, but you can imagine. There may be some interesting curve crossings. Okay, if I squeeze it here, something like this, right? And so on and so forth, right? So we'll have, and I'll show you maybe prettier pictures of this. the second, okay? But that's what you end up with. You end up with these electronic potentials for ground and excited states that are obtained by solving the electronic Schrödinger equation. To solve this equation, you need to write the electronic Hamiltonian, HE. Very, very easy. You just go back to the original Hamiltonian and you pick up the pieces that you need. Kinetic energy of electrons, interactions of electrons among themselves, that's VEE, and also the interactions of electrons with nuclei. So VEN, I believe, that's how I call it. You know, we can, of course, add here V and N, but that's a constant term because I'm solving the Schrödinger equation for a fixed position of nuclei. So it's a constant you can add in the end of the calculation to your electronic energy. You don't have to sort of have it in the Hamiltonian. So, of course, if you have it, then that's all right. I mean, that's not changing it much. Okay. So that's what you have to do at first. What happens then afterwards? Well, you can stop right here. You know, many people do this. What you end up with is you can get electronic wave functions, get electronic properties, dipole moments, polarizabilities. You can compute vertical excitation energies, you know, the differences between ground and excited state energies and things of that sort. But you can go beyond that, and that's important. In my view, that's probably most important. Because once I get these curves, formally, you can prove that these potentials provide potential functions for the motion of nuclei. So now, if you if you start from the time-independent molecular Schrödinger equation, then your what you end up with for nuclei is this. It's going to be the Schrödinger equation for the motion of nuclei, which will have a kinetic energy of nuclei. It will have the nucleus interactions. Of course, that's a potential. But in addition to this, you will end up with the electronic energy for a given electronic state nu as a function of R, as I already described, giving you a potential for the motion of nuclei. And then you solve it for those functions chi. Okay? Please leave some space maybe here, so I'll explain in a second. The result of this will be actually total molecular energy epsilon that we started with, and then chi. And again, you see there is mu here, which means that I can do this for every electronic state. So for every electronic state, I end up with a bunch of nuclear wave functions. Okay, so I will certainly have to label them with a mu. Well, let's do this carefully. Of course, for every electronic state, I'll end up with ground and excited states of nuclei. So I'll use a symbol, let's call it K. Okay, right now. You know, on the picture that I have over there, okay, if I maybe draw it more, let's draw it again. Okay, so you have, say, the ground state, and some excited state, and some other state, and so on, okay? What really I'm saying is that once I have these potentials coming from electronic structure calculations, I can compute various levels that correspond to nuclear wave functions. Those are vibrations and rotations in a molecule. You know, nuclei simply will vibrate and rotate in the field created by electrons. Okay? So that's what you would do. That's what people specializing in raw vibrational spectroscopy would really spend their lifetime on. It's a very interesting area of it. But you can also start from the time-dependent Schrödinger equation. Okay? Well, then you end up with a very similar expression on the left-hand side. So maybe I'll just not copy, but keep it. Well, maybe I'll. Okay, let me actually do it nicely. So what we have on the left is the what we had before, the Hamiltonian acting on the wave function for nuclei. On the right-hand side, we'll have I h bar di chi over di t, simply where chi is a function of r, and in a time-dependent case, you will have, of course, t here. Okay, so that's what we will end up with now. Okay, what is it? Well, if I go to the previous pictures, you know, this will be a situation where I'll have a nuclear wave function, what we often nowadays call a wave packet. Okay, so some sort of let's have a shape here, which will now start moving on these potentials, and you can study this. Okay, so you can see that in chemistry we have this structured sort of system where you start with electronic structure that provides you with electronic potentials, and you use those to simply determine what is the motion of nuclei, either raw vibrations, if that's what you want to know, or the wave packets that tell you how the chemical reactions happen. Because if the wave packet starts going for where it is, suppose I put it up, with some photon, okay, that's what people do in photon-induced dynamics. Well, then the wave packet will start traveling and go here. What happens when it goes here? Your molecule dissociated into A and B, right? Well, that's what you can do, experimentally. Ahmed Zawad got a Nobel Prize for doing such experiments, for example, right? So, and of course, but that's an old story. It goes back to the 30s, in quantum mechanics. But nowadays, people do all kinds of fancy experiments in this way. And of course, I should maybe go back a little bit to this approximation. That's an approximation, of course. The wave function doesn't look that way. The real wave function will be more complicated because the nuclear electronic motions may couple. They couple quite often when you get things of that sort, avoided crossings, where electronic states start interacting, so you cannot assume that you can separate electrons from nuclei. Well then, the wave function gets a little bit more complicated, but you can still use the electronic structure information. So for example, the sort of most general form of the wave function psi, and I'll put it up a little bit, would be not a product, but the linear combination of products. So you would have essentially an expression that would look like you take an electronic state, say mu, okay, that depends on x and parametrically on r, and then you multiply it by the nuclear state, labeled by k, so I'm using the same notation, so chi k mu, which depends on r, okay, and you form a linear combination over all electronic states or nuclear functions involved. So that's a very, in general, it's a very complicated expression. But what I want to say is, and we're not going to, of course, talking about it here. That would be a different course. But I want to emphasize that the Born-Oppenheim approximation is not limited. You can use it directly, as I described. You simply move your nuclei on the electronic potentials. That's just one way to do it. Or you can solve the electronic Schrödinger equation to give you a basis of electronic wave functions to construct more fancy total wave functions, which are linear combinations of these product states, going beyond Born-Oppenheim. And of course, people do this too. Okay? And of course, for nuclei in chemistry, we can also switch to simpler pictures. We don't have to use quantum mechanics all the time. They are so small in size compared to electrons, which penetrate a much larger region. We're talking about nanometers versus femtometers for the size of the nucleus, as you know, right? So that means that quite often we can treat nuclei as point particles and replace quantum mechanical equations for the nuclei by classical equations, Newton equations essentially. Okay, so in other words, quantum chemistry provides electronic potentials, and then you use those potentials in a classical calculation where you move your nuclei, being simply point particles, on these electronic potentials. That is what is called molecular dynamics. As you know, a hugely important area nowadays because you can do this for biological systems, for material science systems, and all kinds of things. So we have all these. And of course we have all these things in between, various semi-classical theories where you have a little bit of a quantum treatment, say for protons which are lighter, and a classical treatment for the heavier nuclei. All kinds, you can have a classical picture with tunneling and all these things. So we can talk forever about this. Maybe I'll now go back to what I have here on my slide. Let's see what I have to do. Lower this, go back, and make this available. Close this one, open the PowerPoint, and from the beginning. So essentially this is a brief summary of what I just discussed, okay? We have an electronic Schrödinger equation, which is a central equation for chemistry, as I already explained, because it is not only a provider of electronic structure information, but it's also a provider of potential energy surfaces for reaction dynamics and spectroscopy. And then you end up, in reality, with these nice pictures. So you can see here, this is, for example, those are a bunch of potential pairs where you break water along the OH bond breaking coordinate, okay, in water. You can see ground state, something that I was trying to sketch there, and then various excited states, okay. You can have these avoided crossings, as I said. That's getting fancier, okay. You can see, this is a three-dimensional potential surface for a system composed of sodium, fluorine, and hydrogen. Here you have sodium plus HF. You follow this minimum valley, you go through a barrier to the product side. So this is how chemical reaction happens, essentially, by moving your nuclei on these electronic potentials. You can do it for ground state, for excited states, you can simulate spectra and so on and so forth. So this is the kind of stuff you want to do in chemistry, all right? But I'm showing this slide for another reason. If you look at the top part, I didn't write the Schrödinger equation the same way I did before, okay? Please note that I split it into Z and V, into two parts, okay? So let's now talk about this for a second. Okay, let me go back here maybe. can I erase these parts? Okay. It's always shout at me if I am erasing things that you still want to see. Okay. So when I look at the electronic Hamiltonian, let's write it now explicitly. Remember there was the kinetic energy of electrons. So we had minus h bar squared over 2 me sum over Laplacians. Then we had minus sum over I from 1 to n, sum over nuclei from 1 to m, and then we have ZA E squared over RIA. That's the electron nucleus interactions. And then we have the electron-electron repulsion terms. Okay, right now I'm writing a simple non-relativistic formula over all pairs of electrons. You see, if you really look at these terms, they belong to two different categories. There is one category here and here, assuming the nuclei are frozen, which depends only on one electron terms. We are summing over one electron terms. That's what I call there as a Z. So I am splitting now the Hamiltonian into the Z part, which is one electron or one body part, and the two body part, the V. Okay? So what is the one body part? It's so let's make sure it is one body. One body means that it's a sum of one electron terms. Okay? So it's going to be a sum over little z depending on coordinates of individual electrons, and you sum this over I from 1 to n. And if you now look by comparing, what is this little z? Well, little z, I already wrote it there, but let's write it also here. Little z will simply be a kinetic energy of a single electron, because the summation over I is buried here. So it's going to be minus h bar squared over 2 me times the Laplacian. And then here, if I take this summation out, I have a summation that describes an interaction of a single electron I with all the nuclei. Okay, so it's going to be minus sum over A from 1 to m is the number of nuclei, ZA E squared over RIA. This is a one electron term, and you sum over all electrons. That's the one body part of the Hamiltonian. There is also a two body part. That is actually the one that causes all the nightmares in quantum chemistry, right? For decades now. We're still waiting, we're still fighting with this term. Okay? That's the two body term. You can see formally, it's a sum of pairwise interactions involving various pairs of electrons that you have. So I can write it as little v, xi, xj, electronic coordinates, and I'm summing over all pairs from 1 to n. And what is v? If I want to follow this recipe, that v here would be little v, xi, xj, would be simply a Coulomb potential involving electrons I and j. Okay? What is essential though here is that there is a structure in the Hamiltonian that I would like to recognize right now. Okay? We can go back to the previous blackboards and we wouldn't be making any progress. We'll be still in the 1930s if we just were looking at those previous equations. We now will stare at these equations in a different way. We'll split the Hamiltonian into the one body part and the two body part. Well, if I do this, I might start thinking, is anybody else doing this? And then, of course, I have a group here of nuclear physicists or chemists, right? And of course, they're doing the same. Okay? Well, this is an electronic part. We already talked about this. Well, you know, Schrödinger equation is the Schrödinger equation. It cannot be different, right? Well, that's the Schrödinger equation for nuclei. You still write it as in a many-body expansion form. Z is the one-body part, which in a nuclei there is no center, right? It's a droplet in space, right? There's no external potential for it. So you're going to have just kinetic energies of nucleons. Okay? Then you have two-body part. I'm calling this V2, not V, okay? I can call it V, I'll call this W. That is just the two-body interaction involving various pairs of nucleons. Of course, the formula is different than this one. It's, as you know, very complicated. Okay, nobody actually knows what it is exactly, but you know, we're making progress. You can use one of the phenomenological potentials like argon D18, CD bond. You can go to the NLO, N2LO, and 3LO series based on effective field theory. Okay, so we already know quite a bit about those. We can write them up and know them, right? Of course, nucleons are not elementary particles. They're not like electrons. They have an underlying quark structure, which means that the nuclear-nuclear interactions are effective. When you are effective, that's like in van der Waals molecules, you may be talking about three-body forces. So sum over these 3-body pieces. And then 4-body, if that's where you want to go. And for example, in NVLO, you already have the first diagrams of 4-body, right? You have 3-body displayed there and so on. So again, the structure is the same. Well, if you think this way, then you can see the only difference between quantum chemistry and nuclear physics, for example, is in the definitions of the little z's and little v's. But those, as you will learn in this course, can be simply pre-computed as matrix elements of the Hamiltonian, stored on a disk or in memory, and then used. So actually, if you have a quantum chemistry program that is written in a generic way for single particle basis, then you can just read 1 and 2-body matrix elements of the nuclear Hamiltonian and fold it. And then this program will think that it's actually computing a molecule when it's actually computing a nucleus. Right? So that's similar. And that's going to be the key here. And we're going to use the language that allows us to do it. So we'll not worry too much about what is the z little v in practice, because we know how to set them up for a particular area, but we'll be trying to bridge these areas together all in one, okay, with the appropriate mathematical techniques. So, well, I guess that's the big statement I'm trying to make. If you learn how to do it in quantum chemistry, you probably know how to do it in nuclear physics and vice versa. And as a matter of fact, kappa cluster theory is an example. That's the theory that was initially suggested in nuclear physics. It became a big story in quantum chemistry because of Piecuch, my supervisor, and Paulus. And, well, our group brought it back to nuclear physics, as you know. So it is now thriving in nuclear physics again. So, you know, that's how this works, back and forth, right? If you start interacting between different areas. There are more similarities. Let's see. I probably will not do a lot more today, but there are more similarities between these various areas of many-body theory, as we often call it. If you look at now the thing is, how are we going to build these wave functions? You know, the fact that I know that the wave function depends on electronic coordinates, well, that's not much of an information. I need to know a bit more about that. Okay? So, well, you can solve the electronic Schrödinger equation or the corresponding nuclear equation using, say, quantum Monte Carlo sampling in the coordinate space. Right? People do this. That's quantum Monte Carlo, a fantastic theory. It gives you sort of a numerically exact, if you do it well, solution of the Schrödinger equation. We're not going to be talking about such methods. We'll talk about methods that use the concept of a single particle state or a spin orbital. Okay, we'll be building wave functions from single particle states here. Okay, and that is sort of based on the observation that if you look at nuclei or atomic and molecular systems, they have typically a very well displayed shell structure, defined by single particle states, which in chemistry we call spin orbitals. In nuclear physics, quite often orbitals. In chemistry, when you say orbital, you mean a spatial part of the spin orbital. There is also a spin part, and so on. And what you do, you know, so I'm showing these shells, you know, for the nuclear physicists, that part is probably very familiar. For chemists, those parts are very familiar. Maybe it's all familiar to all of you. Okay, and then you populate these shells with, say, electrons, if it's a molecular problem, or with nucleons, right? If you have a nuclear problem, and that's how we build wave functions. So let's now try to benefit from this observation. Room control. Go up. Okay. So what can we do? And you know, having this, all of this in mind. So we'll be using single particle states. Before I say anything about them, to describe our wave functions, before I say anything about this, let's sort of recognize certain important properties. We're talking about fermions here. Electrons are fermions. Nucleons are fermions. You know, of course, you know, there are protons and neutrons, but with isospin we can make them identical. Okay? And we know that for fermions, wave functions are antisymmetric. So one condition that we'll have to impose mathematically on our calculations is antisymmetry principle. So the wave function, if I just write the generic wave function, you know, if you say flip coordinates of electrons 1 and 2, okay, let's just do it this way. I guess you don't mind if I don't write these wavy lines, okay? We know that each x, little x means coordinates of a given electron. Well, then you end up with minus minus psi x1, x2, xn. Okay, so in general, if I permute my, say, electronic or fermion coordinates using permutation capital P, okay, now I'm trying also to use this as an opportunity to introduce various notational things. So if I have a permutation that brings indices 1 through n of our fermions into P1, P2 up to Pn, okay? So these P's are here simply a permutation of original symbols. Then, the general formula would be that if you simply permute your fermionic coordinates, so you have x, P1, P2 up to Pn, it's a capital P, we end up with sign of this permutation, which I will always write in this course as minus 1 to the P. It's not minus 1 to the anything, we just need to know the sign. It's plus or minus, okay, times psi of with the original set of, or original ordering of fermionic coordinates. And so that's how I'll be writing permutations if I need to do this. We'll use them in Wick's theorem, for example, in contractions, so this is important now. How do we determine the sign? Maybe all of you already know it, but just as a reminder, essentially the easiest way is to simply split a permutation into the product of cyclic permutations on non-overlapping sets of indices, and then determine the sign from there. So for example, just let's have an example. If I have, say, 5 indices and I want to permute them into, say, 2, 3, 1, 5, 4, I just have to look at, I want to know what is the sign of this permutation. Okay, well, I can see that 1 becomes 2, 2 becomes 3, 3 becomes 1 again. So you have one cyclic permutation, and then you have 4 becomes 5, and 5 becomes 4. That's another permutation, which we often describe as a transposition of the indices. So there's another word for it. And the rule is that if a cyclic permutation operates on an odd number of indices, the sign is a plus. So that's the it has a quality of plus. If it operates on the even number of indices, it's a minus. And the overall sign is just the product of these signs. So you can always figure out, so here it's going to be minus for this one. So then minus 1 to the P will be a minus if I use that permutation. Okay? That's what I'll be doing in various applications. So now, with all of this, what can we do about our Many-Fermion wave function? Well, I'm going to be trying to build it using single particle states. So let's introduce them. I will use letters little psi. So remember, when I say little lowercase psi, that means a single particle state. Capital letters will be reserved for many body states, just to keep some organization here. So, and I'm going to right now label them with little p's. I hope that this is little p for you, and that one is a capital case P. If not, please ask me. It's a function of coordinates on a single electron. So that x here means x, y, z, and spin if it's an electron, or the corresponding coordinates of a nucleon that you would be using, various quantum numbers, the L's, the J's, and the M's, and all these things that you need to describe a single particle state. Okay, we're going to be using often Dirac notation, which I'm assuming all of you are familiar with. Or you can say, well, what's the purpose of little psi here? I guess in the Dirac notation, not much of it. So you can just drop it and write it also as xp. So if you see this, what I mean, it's a single particle state p computed at x. Okay, that's all I mean. And we will assume that these single particle states, or spin orbitals are orthonormal. Okay, so in other words, if I set the condition psi p inner product of psi q, written, I'm going to be writing this sort of multiple times, okay, in different ways, so that you're going to see various types of notation I'll be using here and there. So I can also write it like this. If you want to be more explicit, it's an integral of psi p star x psi q x integrated over coordinates of a single electron. That's how you would compute this matrix element if you really wanted to do it explicitly. Okay? And we're assuming that it's an orthonormal set. So that's delta P2. We'll be assuming that our spin orbitals are normalized to unity and orthogonal. Okay? And in the exact theory, you would have infinitely many of them. In an approximate calculation, you would consider some finite number, say 500 or 1,000 or whatever your basis set provides. So we'll be talking about this later. Okay? We also assume that this is a complete set. So if I take any function of a single, say, electron or a single fermion, I can always write it as a linear combination of these little psi p's. So say some coefficient Cp psi p, okay, sum over p. I'm not going to write the range because the p can go from 1 to infinity or whatever is appropriate for your basis set. Okay, We also, of course, if I use the Dirac notation, I probably would write it like this. The one electron function, one fermion function is just a linear combination of the single particle states. Okay, how do you determine coefficients? When you go back to your quantum mechanics classes or theory, whatever classes you took, maybe mathematical physics or Hilbert space theory or any of these, then you know that Cp from orthogonality and completeness is simply an inner product of the spin-orbital p and psi. So again, explicitly, if I want to know it, it's just an integral of a given basis state psi p star x integrated with our function psi that will expand in this way over all electronic, over the coordinates of, say, a single electron or a single fermion. Okay? Now, of course, there is always a practical aspect. How do you get these spin-orbitals? Okay? So in chemistry, spin-orbitals are often written as, I'll just write it here, spin-orbitals are often represented as products of spatial functions that depend on x, y, z of a given electron and the spin state, which will be spin up or spin down, the alpha or beta states. So that's why we say spin orbital. Orbital times a spin function, it gives you a spin orbital. Of course, in nuclear physics, that's going to be something else. But still, you will have single particle states. And where do they come from? Well, in chemistry, quite often they come from some mean field calculation, like Hartree-Fock. It will be a provider of single particle states. You can use some other forms. You can use constraint DFT. You can use Bragner field, and I'll discuss here. You can use multi-configurational Hartree-Fock. There are lots of ways to generate orbitals. In nuclear physics, you can also use Hartree-Fock. That has a little bit of a caveat, right? Because you break one of the symmetries, the central mass problem, right? But you can still use them for any nuclear. That's okay, all right? And you can also use harmonic oscillator functions, of course. That's the popular choice. Okay, so we know how to generate them. This course is not about this. There is already a well-developed industry of generating single particle states out there. Okay, for us, they will be a basis for constructing the many-body wave functions. So I guess since my time is up, I'll start the next lecture with telling you how we're going to represent now the many-body wave functions in terms of single particle states. Okay, some of you may already know it. We'll use later determinants to do this, and then we'll start talking about switching from the language I'm using now still, the old-fashioned sort of language of first quantization, to the better language of second quantization. Okay, which will allow us to go much further beyond in our considerations. If you go back to what I started, you can see that everything I wrote here depends on the number of electrons and the types of nuclei and their number. If I wanted to solve this equation like this, or even the electronic one, we wouldn't be making much progress because you would have to go system by system by system. One calculation for helium, another for lithium, another for lithium hydride, another for hydrogen fluoride. Every time you have to redo the calculation from the beginning, right? We're going to be switching the language. We'll switch to second quantization in chemistry. It's important because then you end up with a formulas which is partially independent. Okay? The equation will look the same for various types of particles in your system, and we can even be able to change the number of particles. Ionize our systems. Okay? So we'll do this next time. Thank you very much. I'll see you on Friday.